Today we are going to talk about innovative small incremental forming machine with eccentric cylindrical slider tool mechanism.
Inspired by the intricate shapes of consumer products like chocolates, this project develops a compact single-point incremental forming machine. The system fabricates custom metal molds from breadsheets using a tungsten carbide spherical tool to induce layer-by-layer plastic deformation, eliminating the need for expensive dies. This study utilized single-point incremental forming, where a spherical tool induced plastic deformation through a layer-by-layer pressing process. Given the critical nature of the tool, we used a tungsten carbide was selected for the forming pin to ensure durability. The pin was precision machined using a diamond grinding wheel on a lathe. To meet the requirement of the compact machine, we use a 28-step stepper platform as a drive mechanism combined with stretchable brakes with a tensile strength of 350 Newton meter. The maximum step size per increment is 0.457 millimeter, about half the diameter of the ejector pin. The design of the ejector pin is particularly critical, and it must withstand forces in both forward, backward, and lateral forces. Unlike conventional designs, the rotational axis of the lead screw in our designs doesn't combine with the center of the slider, which satisfies the Abbe principle by reducing measurements and alignment errors related to larger offset distances. Judges, please observe behavior by manually rotating the mechanism.
The overall mechanism design includes the eccentric top column slider mechanism and motors for the S, Y, and Z axis. Because Y axis was located the lowest position and therefore bears a large load, two motors were used to share the load. The circuit system is an improvement on 3D printer that we built for the school activities. It includes Arduino 2560 control board. The XY axis was driven by 28 stepper motors coupled 15mm slide, and the axis was a 42 through shifter stepper motor. All motors were driven by A4988 chip. Parameters were added into the chip using Marlin 2.0, and assembly was complete. We first checked the positioning accuracy of our mechanism by testing the displacement of S, Y, and Z axis. For the Z axis, a dial indicator were used to measure vertical travel. The tool consistently returned to a zero datum after linear movement. The maximum feed rate set to 1100 mm and 100 for the S axis, 1000 for the Y axis, 400 for the Z axis. To evaluate the plastic deformation capabilities of tungsten carbide tool. We did incremental step and we did incremental step tests using vertical step increments 0.1 millimeter. We test the forming speed ranging from 50 to 300 millimeter per minute. To balance we can discover the lower speed enhance deformation quality. To balance the deformation and the production quality and production efficiency. Also, we conducted experiments to determine the maximum tilt angle based on the law for volume constancy. The deformed is defined by T2 equal T1 cosine theta.
We used master can to develop two paths stretched custom by our 45-degree maximum wall angle. With 3D beautiful modeling function, we generate 3D control. Additionally, we developed a Python-based workflow for enhanced accessibility. The system covers simple beam measuring into vector graphics and then translates them into G-code. To sum up, we successfully overcame technical challenges to deliver a machine that meets all design goals. This result demonstrates the system's strong potential for common practical application and customized manufacturing. As to how our machine works, you can see that the ball head is now placing the metal sheet using the intermetal forming method. Below, you can see the lead axis essentially top here, the SY sliding platform, and the self-made mechanical parts. The finishing products are made for our various experiments. Thank you.